Okay, so welcome back. And so in the first lecture, we talked about concepts, but then proprietary solutions. And in this lecture, I'll tell you something about ongoing standardization. So there are several different standardization bodies that are active in this area. So if you take this picture that we saw before, the first body is Trusted Computing Group, which is a body that has been standardizing this TPM, Trusted Platform Modules, and Trusted Execution Environments primarily for personal computers for a long time. They and the US NIST, National Institute for Standards Technology, have specifications that talk about these different types of hardware trust roots. So a trust root is, you already saw examples of that, like a verification root, or trust root is what you have to unconditionally trust in order to build up trust in the rest of the system. There are also standards for secure boot. The most common one would be this UEFI, which is a standard that's intended for PCs, but for example, Windows phones also use this. That tells you how to go through a secure boot process. We saw Trusted Execution Environment standards. The trust zone is a de facto standard, but there is also global platform that's now specifying the API. So they don't specify how to design a trusted execution environment, but they try to specify how to write a trusted application that will be independent of a specific kind of trusted execution environment, so that in addition to ARM trust zone, you would be able to write a trusted application that can use either ARM trust zone or maybe Intel's trusted execution environment or somebody else's trusted execution environment. So global platform has been doing this. They standardize this interface. They also standardize the interface for applications. So one could argue whether this is really the high-level API that applications should use, or is it like an API that's actually meant for the operating systems use. But there's a global platform standard for this interface, and Trusted Computing Group has its own standard for applications. So I think somebody said that about standards, that the good thing about standards is that there are so many to choose from, and that might be the case here. So I'm going to briefly talk about the other standards like UEFI and so on, but I'll tell a little bit more about global platform and then spend the bulk of my time in this TPM 2.0, which is the new version of the Trusted Platform Module, because it has a very powerful authorization mechanism that on the one hand it's very flexible. On the other hand, whenever something is very flexible in security, you need to be worried about that flexibility. So UEFI, I'm not going to talk too much more about that, but UEFI is a replacement for the BIOS standard. It has secure boot as an optional feature, and secure boot is, you remember that every stage of the boot process you can pass or fail depending on whether the next stage conforms to some known good value. And the way they do that is they have a, or maybe it's visible in the next slide. So they have a bunch of signatures, a bunch of keys that are allowed to sign known, that are allowed to sign acceptable operating system images. And essentially, when you boot a program or boot a kernel, you have to have a signature from the accepted list. So like I said, I'm not an expert in UEFI, and other than Windows Phone, UEFI is not used by mobile devices. So I just want to put there for completeness, but I will go on further to the other standards bodies. So NIST, it's not a standard in the sense that they don't dictate how something should be done, but they rather try to clarify the different types of trust roots that should be on a device to be able to build up the kind of trust that we talked about. So they call them roots of trust that have been implemented in hardware, and they identify a bunch of different roots of trust. Like roots of trust for storage and for measurement, verification, integrity, and reporting. So maybe the best way to understand these different roots of trust is to actually map that to the the figure that we had in the beginning about what constitutes a TEE. Right. So if you remember, we had a picture like this. So there's some animation problem here that this is missing. So roots of stuff for storage. If you want to build secure storage, then you have to unconditionally trust the device key that it's protected, and you have to trust the cryptographic mechanisms. Right? So that constitutes the root of trust for storage. If you want to measure what you are going to boot in terms of authenticated boot or secure boot, that's called root of trust for measurement. And you have to trust the boot sequence, you have to trust the volatile memory where you store the measurements, you have to trust the cryptographic mechanisms that you use to make those measurements, like hash functions or iterative hashes. If you want to verify code that come from outside, like the secure boot, then your root of trust for this verification again depends on the verification root, the public key, for example, and the cryptographic mechanisms that you would use to verify the signature. Root of trust for integrity. So once you have measured, you want to make sure that what you are running is the same thing that you measured before. Relies on the fact that where you store the measurement should be, the integrity of that should be protected. So the volatile memory is the root of trust for integrity. If you want to report this information to a third party, then you have to rely on the volatile memory where you store the information, but also the device key that's either going to sign the report or that's going to protect the key that will be used to sign the report, and the cryptographic mechanism that you actually use to sign the report. So NIST actually identifies this kinds of thing, and that is more for like conceptual clarity, that if you are going to rely on build a system like this, then you have to know which parts you are going to trust unconditionally for that particular purpose. So if you care about storage, you have to trust certain things. So let's talk a bit more about these two standards bodies. This global platform, which is the essentially the standardization organization for trusted execution environments first, and then we'll talk about this TPM. So global platform has a heritage from smart card standards. So they are the ones who develop standards for these payment cards, not payment cards, but the tickets, like for transportation tickets. I think they also do standards for point of sale terminals and so on. But they have a recent group called the Device Working Group, which is sort of taken on the job of developing standards for mobile devices. And so you can, their website is called globalplatform.org, and you can find the various standards that are public so far. And the ones that we will talk a little bit about are the overall system architecture. So the picture that I showed you earlier, like REE and TEE and so on, they are taken from their standards, the system architecture standards. They also have these two APIs, the API for writing trusted application and the API using which applications can use the TEE functionality. Those two APIs are also public. And then they have a standard for this trusted user interface. How can a user know that they are interacting with a trusted execution environment? That's I would say that they are not at the same, that's not at the same level of maturity as these two other standards, but they're all relatively new anyway. Okay, so if you take this picture from before, the first standard, which is this internal API, like we discussed before, this is a way to write trusted applications that are independent of the specific type of TEE. So essentially, you can think of this as the libc for trusted applications. So it gives you, the internal API gives you all the functionality that you would need to write a trusted application, so cryptographic APIs and memory management APIs and so on. Once you have your own trusted execution environment that conforms to this internal API, then the intent or the idea is that any trusted application that conforms to global platform standards would be able to run on your trusted execution environment. The other client API is sort of roughly here, which is meant for operating system applications to be able to invoke some trusted application and give it parameters and get the results back. And the trusted interface, user interface, is somewhere here, that it's user interaction from trusted applications done in such a way that the user can see that they are interacting with the trusted application and not with the rich execution environment. So the way the way an application runs a trusted application, the normal application runs a trusted application, is we already sort of alluded to this before, that the application sets up the information in its own memory. That sets up the actual trusted application code and the input parameters, and then it asks via the supervised and the rich execution environment, it transfers control to the trusted execution environment, which will launch the correct trusted application, and the trusted application has access to the memory. So sometimes the trusted operating system might actually copy some stuff from here to the trusted application memory, and sometimes, depending on what you are doing, the trusted application might actually have direct access to the memory of the original application. So if you are dealing with, say, bulk encryption, decryption, it wouldn't make sense to copy from the application memory to trusted execution environment memory, but rather give access to the trusted application to the main memory so that it can do in-place encryption, decryption. So the client API, so this is the API that you see here, is actually very simple. So it doesn't really understand anything about trusted applications as such. It essentially gives you a pipe to open a channel, say I want to run this application, and then invoke commands in that application. So you set up an application that you want to run. You set up input output parameters. The trusted application is supposed to be structured in the form of commands. So every trusted application will support some named command, some set of named commands. And the client application would say, I want to invoke command number 3, and here are the input parameters. So if you look at the client API, it essentially consists of something like 10 functions. It has functions that sets up this communication channel, so initializing a context and allocating shared memory so that the trusted application can access it. And then the real meat is in a very generic command like invoke command. So you say, I want to invoke a command in this session, and the name of the command is such and such. So the client API is essentially unaware of the semantics of what you are trying to do. So it doesn't know things like sign or decrypt or run the state machine of some client-side protocol. It only knows to talk in terms of commands that are provided by the trusted application. On the other hand, the trusted application is the one that has to actually implement these commands and use this very extensive internal API, which, like I said, is like the libc. So it has to also have ways of setting up the channel and so on, but then it has to have a big switch command, switch block that would say, here are the commands that are exported by this trusted application. So in order to use a trusted application, rich world application has to know what commands it exports, but the client API implementation doesn't have to know. It just knows that there are some commands. The internal API gives all kinds of functionality. So for example, there are APIs for secure storage. So you can do things like create a persistent object, read and write, seek, truncate, all that. There are also internal API methods for trusted applications to communicate with each other, so that a complex operation can be done jointly by multiple trusted applications. And in addition to that, there is like a crypto library. You can make use of time and arithmetic and memory management and so on. The trusted user interface API, which is the third API that I mentioned, in a sense, what Global Platform does is like essentially a kind of a cop-out. So it says that there's a rich execution environment and the trusted execution environment. Trusted execution environment can have its own API for its own trusted user interface, and then it just specifies that what you can do with this user interface. So it sort of looks like a graphics library that you can have keys and you can put buttons and so on. But it assumes that this whole thing is physically separate from the UI that the rich execution environment would use. So if you remember the question at the end of the previous session, somebody was asking why couldn't we have even an LED? Something like this is going to be unlikely, that you would have a dedicated UI for trusted execution environment. This could happen. So for example, I think there are several companies are thinking about having, for example, a back cover that has its own display, maybe a bistable display, like an ebook-like display that will be only accessible to the trusted execution environment, and it will be clear to the user that they are dealing with the trusted execution environment. But I think the real challenge would be to figure out how to use trusted UI while sharing the same display and same inputs with the RE, because I think that's what is realistic in a market like this, where it's unlikely that the cost of a separate trusted execution environment will be paid for. And the standard currently doesn't do that. So I also don't know if anybody is implementing this this trusted user interface API for this same reason. So there is a fourth. It's not a standard; it's a white paper. So there is this problem of how does a trusted application get into your device, right? So this is the problem that the onboard credentials project was trying to solve. Like I said, this global platform and the people who make trusted execution environments, they come from a smart card heritage, and their model for provisioning is that there is a central authority that controls provisioning. So if you buy a device, and if I want to deploy an application and some credentials to your device, I have to go through the central entity, which is the one that has the authority or the rights to install and manage trusted application on your device. So this is, you can call this issuer-centric provisioning. Actually, global platform uses this terminology of issuer-centric provisioning. There's an issuer who is authorized to manage applications on a device, and the whole provisioning architecture is centered around this issuer. And what we try to do in OBC is to say the provisioning is anybody can provision as long as the user agrees. And they have a white paper that talks about this idea of user-centric provisioning. I think everybody sort of realizes that this issuer-centric provisioning is maybe not the way to go towards the end for the reasons that we talked about, but also we have this kind of app store model, which works very well in the normal operating system, right? So rather than having trusted applications and rich applications come from different sources, it might be that a rich application might have a trusted application embedded in it. And then trusted application might come from different sources, different app markets, for example. So they have a white paper. They don't have a specification yet. But essentially, they are trying to address this problem that if you have a user and you get your trusted execution environment, which is like could be a separate token like a smart card or USB, or maybe your device, maybe your phone. So you get that from one source. And the current model is that you have a service provider who wants to send you a trusted application, and that comes via some kind of service manager. And how to get rid of the service manager and say that this user can get trusted application from any service provider. That's the sort of spirit behind this user-centric provisioning, but there is no standard for this as yet. The kind of history is that it used to be the case that when smart cards, especially Java cards, did not have an onboard bytecode verifier, it was essential that the code that comes to your device is somehow trustworthy and authorized, because the Java card semantics cannot be enforced if you don't have a bytecode verifier. So somebody has to say this bytecode is trusted, and therefore you can run it on your device, and you don't have to. You can rely on this bytecode to not violate the language semantics, like a private variable stays private. So this was the reason why some kind of centralized provisioning was essential for the security of provisioning systems, that somebody has to say that this is good code before you can run it on your device. If you have a on-card bytecode verifier, or if you are not using Java but you are using something else, then that's not essential, right? So you don't need the centralized provisioning for security. But centralized provisioning has other advantages. It gives control to whoever is provisioning it, and it might also have usability advantages, as we might, if you have time, we might talk about later. So just to give you an idea, if you have a device and you have these credentials that come from different sources, and you want to you lose this device, or you want to buy a new device, then you want all those credentials to move to a new device, right? If you have a centralized provisioner, this is very easy. You just tell the centralized provisioner that you have a new device, and they will re-provision everything. If you have this kind of very open provisioning model where you can get credentials from all over the place, then it's not evident what the user is going to do to be able to move all the credentials from the old device to the new device. So there might be also usability advantages in having a centralized provisioner. So in the case of global platform, this is an open area now. The only provisioning that's available today is the centralized provisioning model. And this is the other reason why you don't see arbitrary developers being able to write trusted applications, because even if they could write a trusted application, even if they could have the right SDKs and so on, they wouldn't be able to provision this application to your device without the collaboration of this centralized entity like the provider of the trusted execution environment. But whether that will change with the user-centric provisioning or not, that remains to be seen. Okay, so I think this is, I already said most of it. The specifications provide the basis to be able to write trusted applications. There are some issues like user interaction, but the access and the provisioning is still centrally controlled, and whether that changes or not remains to be seen. So I can maybe take this moment to sort of plug a project that we have been doing now. So we have I have a student who essentially took this internal API and implemented that in software. And this is a GitHub project. It's funded by Intel, but it's open to everybody. So anybody can participate in that. Initially, we actually thought of this as a developer tool, right? So if I'm a developer and I want to write a trusted application and I don't have a hardware trusted execution environment, having a complete software implementation will allow me to debug through a trusted application, plug that into my favorite IDE, and once I have the trusted application developed, I can then compile that to whatever target environment. So we thought that this will be good for developers and researchers. So we as researchers would like to, for example, experiment with new provisioning mechanisms. If you don't have a hardware trusted execution environment, but to have a software emulation like this, that could be also useful. But it turns out that this might even be interesting as a kind of fallback trusted execution environment. And this actually came from one of the groups that we are collaborating with, which is responsible. It's called the Finnish Population Registry. So this is the entity that specifies how citizens and residents of Finland can authorize themselves to government services like the filing a tax return and so on. So 10 years ago, they tried to issue smart cards. So you can actually go buy a citizen smart card that proves that you are a citizen, and you can use that to authenticate the government services. That never really took off, because in order to use that, all the entities that want to authenticate you either have to have a smart card reader, or you have to have a smart card reader that you can connect to your PC. And that, of course, is a cost and it's a barrier. Later on, they tried to do that with SIM cards, so that you can actually have a certificate and your key pair in a SIM card and then have it certified as a citizen thing. But that also didn't really, so it remains to be seen whether that will succeed. But there are multiple operators involved, and it's not clear if that will go far. So what they are interested in is to be able to see, can they, so essentially what they need is a key pair and a way to protect a key pair and say this key pair identifies you as a citizen, and if it's protected by your mobile phone hardware, then you can use it to authenticate back to government services. So they would like to use this, except that if they want to deploy a solution, like if they want to say here is an application that you can download and install in a device, and you can use it to authenticate back to us or back to any other service. So for example, in Finland, online banking uses this kind of a one-time code authentication to banks. The same system is also used by others. If you want to buy a movie ticket, you can use the same authentication mechanisms to authenticate a theater and buy a movie ticket. So once you have a citizen and resident authentication mechanism, it can be used not only for government services but also for other services. So if they want to deploy an application like that, they would want this application to work the same way to the entire user base. Maybe some of them will have the latest Samsung phones and iPhones that have hardware TE, but the bulk of the rest may not initially have this hardware trusted execution environment, or they might have it, but the applications might not have access to it because these APIs are not deployed yet. So they would want a system whereby they can send the same application to all their user base. The application would detect If there is hardware, if there is, it would use that. If not, then it would use an emulation like this. But the fact that they are using hardware or they are using an emulation could be sent or informed back to the service provider by using some kind of device authentication attestation. If they could do that, then they could provide sort of different levels of service. So for example, if you're using it for online banking, you could say if you're using a hardware TEE, then you can actually access your account and make payments and whatever. Whereas if you're using some software TEE and you just have only ordinary user authentication, maybe you can just view your account but can't actually make any transactions. So it turns out that if what we thought as a developer tool might actually be useful as a TE replacement as well, that it can be used as a fallback TE. And this, of course, brings in other considerations. So when we are thinking of it as a developer tool, we were not thinking about the security of this implementation. It's just a C library that you can link to your trusted application. Now we have to think about what kind of isolation can we provide so that there is some guarantee of security. Of course, it won't be the same level as having hardware, but if we can bring it to the level of the security guarantees provided by the operating system, that would be good. So we haven't really gone that path yet, but what is there now, this is work in progress. What is there now is a complete implementation of the internal library. And like I said, anybody who is interested, of course, this is a GitHub project, so you can contribute to it as well. What we hope to have in a couple of months is a full sort of end-to-end system where you can debug an ordinary rich application, and at some point it calls a trusted application, and you'll be able to go to the trusted application, single step through it and debug the trusted application as well. But we are not there yet. Okay, so with that, let me come to spend the rest of the time talking about this trusted computing group and the standards that they develop. So trusted computing group is not a mobile specific organization. They are actually primarily specifying trusted platform modules and associated services for PCs and servers and so on. But they've had a mobile working group for a few years now. And the new version is such that it's designed to work, not have separate standards for PCs and servers and mobiles, but have a sort of generic standard that can be easily adapted. So you can have like an instantiation or a profile of a TPM2, which will work on mobile devices as well. So I don't know how well people know trusted platform module and trusted computing groups. I'll provide a very quick overview, but if something is not clear, then you can interrupt me and ask me. So trusted platform module, which is the core of this trusted computing group set of standards, is essentially a discrete TE, and it does a bunch of things. So it can collect information about the state of the system. So you can measure the operating system and bootload and so on, and can store that in the TPM. And it can be then used for things like remote attestation, that you can report the state of the system to some external party. Or you can use this state information to control access to resources that are protected by the TPM, like for example, a signing key or a decryption key. And so the TPM resident keys, so it provides functionality for generating a key and using a key. It provides functionality for storing some data, encrypted and integrity protected outside the TPM. And it provides essential cryptographic operations. So an integral part of this TPM specifications is this idea of what's called platform configuration registers. So if you remember, when we talked about authenticated boot, we said that at every stage the verifier component measures the next stage and stores this information in an integrity protected memory area which represents the state of the device. So PCRs is essentially a way to store this kind of state. So it can have information stored in the PCRs are essentially volatile memory, but they are integrity protected. So there is a definite way in which you can add or change the information that you store there. And at any time, a PCR represents the sequence of changes that you have made to the PCR. And so in order to do this, of course, you have to trust the place where you start, and that's, as we saw, it's called the root of trust for measurement. And once you have a root of trust for measurement, the use of PCR looks something like that. So you have a root of trust for measurement, which is like the BIOS or the UEFI bootloader. So that's going to boot a piece of code, which might boot another piece of code like the operating system, which might then launch an application. So at every step, you take you measure this piece of information and then add this to the state information that you are keeping track of in a PCR. And the way a PCR is updated is a kind of an iterative hash. So you have some current value of the PCR, which is called HOLD. You have a new measurement, which is the piece of code, or it doesn't need to be code, it could also be hardware. Something that you measured, some component that you measured, which is part of the system state that you want to remember. So you combine this current measurement and the new measurement, and you apply a cryptographic hash function, and the result is the new measurement. So in this particular case, initially the PCR starts with an initial value which is 0, and as you keep loading these, if the measurement of this one is M1 and if the measurement of this one is M2 and this is M3, you will end up with a value like this, which is what I call iterative hashing. So after you have booted this up, the value of this PCR represents this current boot sequence. And what this means is that if you have a PCR value at the end of this boot, there's only one way, assuming your cryptographic hash function behaves like a cryptographic hash function, there's only one way you can reach one sequence of events that will get you to this place, right? So now you can use this for various things. So one of the primary uses, there are two primary uses that we talked about: remote attestation and secure storage. So in remote attestation, the way this would work is there's a verifier that wants to know what is the state of your current device. So he can send a challenge, a random fresh challenge, and the attestation is you take a PCR value. Later we'll see that it doesn't have to be one PCR, you can actually have multiple fixed number of PCRs that represent the state of the system, but let's think about one PCR. So he has a PCR value that has this iteratively generated hash that represents the system, and the TPM then constructs a response to this challenge which binds this challenge with the current PCR value, and that is signed by a key which is unique to that TPM. So AIK is called the attestation identity key, and TPM specification tell you how this can be initialized and how this AIK can be how a TPM can be certified by binding it to this AIK. But once you have this and you have a root of trust for measurement from which you can actually measure the current state of the system, you can report this fact to a third party. So that's one use of PCRs and the state of the system that's captured by the PCR. The second use is what's called sealing. So this is the case where you want to store something, some secret information, and you want to say that this secret information is available for use only if the system is in a certain configuration. And this could be, for example, you can separate between creators. So let's assume that there is a RSA key pair PKSK that's created when the system is in a certain configuration, represented by a PCR X. So there are multiple PCRs, but one particular PCR has a certain value, and that might be the result of booting a specific operating system like Windows 8 version blah blah blah, and having run a certain set of applications. So that's captured by this PCR value, and when the configuration is at that state, the application or the operating system creates a key pair, and now it can tell the TPM that I want this key to be accessible only when the configuration is exactly the same, right? So if you remember, this is like authenticated boot. If you booted something else instead of booting Windows, if you booted Linux, everything would work fine, except that the Linux configuration wouldn't be able to access this key because the PCRx value will be something else, because the measurement would have changed in some part of the chain. So these private keys are then stored. This is like a secure storage thing that we saw before. You have some secret information. In this case, it's a secret key. But you store the secret information bound with this kind of access condition. So this says that this secret key is allowed to be accessed only when the PCRx value is such and such. So remember that the secret key is the PCR is inside the TPM, and it's not modifiable by the outside. And the secret key itself is not, of course, stored inside the TPM, because we want to be able to store arbitrary secret information. So it uses a secure storage construct like this, where there is a storage root key, which is what SRK stands for, which is like the device key that we saw earlier, that is unique to the TPM, is available only within the TPM. And TPM can use that to protect not only this key, but also the access condition by doing an encryption of these two together, maybe an authenticated encryption, and then give it to the operating system to store outside. And then whenever the operating system wants to use it, it can provide this sealed storage, and the TPM will, of course, it will be able to unwrap this so that it can get the SK, but it will also get the access condition. And then it will allow the key to be used. For example, if it's an RSA key, the use might be via a sign function. They allow the key to be used only if this PCRx has been has reached a certain value. And as we saw earlier, it will reach that value only if you follow the same exact sequence of PCR extensions. If you booted the system in a specific order, in a specific way. So this is how TPM, the standard TPM works. And as you can see, this is on the one hand, it's a powerful mechanism. On the other hand, it's very brittle, right? So if you create a key, and the key happens to be created when you were running a certain version of Windows and certain bootloader, that key is accessible only if you boot the same version. If you make a change, if you have a new version of the bootloader or a new version of the operating system, the PCR value will not be the same, because it will have a different measurement. And any change in the measurement in the chain that leads to the final PCR value will lead to a different PCR value, right? So in that sense, it's brittle, in the sense that every time you want to do an update, you have to have different ways of some way to migrate PCRs from the guard PCR value like this, from the old value to the new value. So when TCG became interested in the mobile space, and they started a working group called the TCG Mobile Working Group, and they wanted to see how these TPM specifications can come to the mobile devices. They had to deal with a bunch of issues or problems, and then this brittleness is one of them. So the first problem is, of course, that to answer this, they created a new specification called Mobile Trusted Module, or it's also called TPM Mobile. And the first issue that they had to deal with was the fact that mobile devices already had these trusted execution environments like trust zone. So if you want to define a TPM and then say the TPMs would be like in PCs, which will be an external separate module, that's not going to be realistic here, because why would a mobile device manufacturer spend the money to deploy a new hardware element when they already had similar functionality that was already deployed for the reasons that we talked about before. So the first change they made was to say you can realize TPM as a virtual construct which is protected by these trusted execution environments like trust zone. So this is one. The second one was mobile devices, and actually any device for that matter, but mobile devices was a particular case, is that there are multiple stakeholders. There are drivers that come from different sources. The hardware elements might come from different sources. So if you wanted to do secure boot, you have to make sure that your secure boot mechanism caters for these multiple stakeholders. So the kind of a brittle mechanism that we had in TPM 1.2 wouldn't work. So if I have a processor that loads a driver that comes from a different manufacturer, the driver manufacturer should be able to change the the driver version in a controlled way, and my secure boot should still succeed. So TPM and the PCR construct as it was in 1.2 was simply not useful for the use of in mobile devices. So they came up with this first idea that rather than having the strict chain, it should be possible to deviate from the strict chain so that access to a resource can be authorized not only via one particular way, but via a number of different ways, but all of them in a controlled manner, right? So the example or the motivating example would be that the mobile device has to load a driver, but the driver comes from a different supplier, and we want to be able to let the driver supplier release new versions. Secure boot should still succeed, but of course if some other driver is used from a third party, that should fail. So we want to be able to allow these multiple paths that were not known at the time when this secure boot conditions were made to still succeed. So they introduced a notion of what's called reference integrity metric certificates, and that said that rather than updating the PCR in this particular way, there is a way to break this chain while not compromising its security. And essentially it works something like this, that it says, so maybe in the picture we can say, if there is a PCR like this that has some old value, then the way to update is not just adding the new measurement and extending it in a particular way, but we can say if there is a external entity that certifies that whenever the PCR has some old value, then we can replace that or replace some other PCR with a new specification that says you add a new measurement to that PCR. So this essentially says that you have to say the way to update this PCR depends on some verification key that's part of the root of trust, and if this verification key allows, then this PCR can be updated in a way that deviates from the normal way of updating PCRs, right? So this would make it possible that you can still have secure boot, and you can say the secure boot is and you can actually make use of the secure boot or authenticated boot. You can say there's a key, that the key is protected by an access condition that says the PCRY should have this particular value, but we can say that this particular value can be reached by different boot sequences that are all authorized by having an external entity issue a certificate. So whenever there's a new version of the driver, all this external entity has to do is to issue a new certificate that has the measurement of this new driver, so that when you load the driver, this will get the right measurement, and this certificate would say that can be now mapped to this value that is expected by the key pair. Okay? So this was like the first attempt to address this brittleness question, that you can associate guard conditions with secure storage or other resources and have multiple ways of reaching them. So what TPM2 does is to just take it to the logical extreme. So it has many other improvements. So TPM1, for example, did not have algorithm agility. They use SHA-1 as the only way to extend PCRs. I think they only had support for RSA 2048 bits. Now they have mechanisms built in so that you can actually update the algorithms on. But the main two main things that change from TPM 1.2 to TPM 2.0 are in some sense motivated by these mobile use cases. So the first one is that it's no longer the case that TPM 2.0 has to be a discrete physical entity. It can be realized in software, as long as you can base that security of the software implementation on some other underlying hardware root of trust, like this trusted execution environment. That's number one. The second one is that they change the way TPM enforces access control, so that in order to protect a resource, you can now not only deal with PCRs like we saw before, but have a very flexible way of doing access control. So before I actually start explaining this TPM 1.2 access control once again and how that relates to TPM 2.0 access control, the envisioned way that TPM 2 will be used in a mobile device is that on the trusted execution environment, you use TPM as a trusted application, and the applications in the operating system side they don't have to be aware that they are dealing with trusted execution environments as such. They think that they are using a TPM, except that the TPM, so they will use the TPM 2.0 interface. The TPM is realized as a trusted application, so underneath you go through the same kind of TE invocation that we talked about before. So this is kind of one way in which TPM2 will be used in or could be used in mobile devices. But let me just step back and try to explain to you how access control is done in TPM 1.2 again, and how TPM 2.0 just changes this, makes it much richer. So in TPM 1.2 we had like a system, and inside the system there was a TPM. TPM was protecting objects. An object could be an RSA private key like we saw before. And the objects are used by some object invocation. So if it's an RSA private key, you might want to use it by issuing the TPM command that says sign with this private key. And these object invocations are subject to this object authorization check. And in the case of a RSA private key that is sealed for a particular configuration, the authorization check would check these reference values. Right? So it could say this PCR or this set of PCR should have these values, and if that's the case, then this object invocation can succeed. Okay? So in addition to that PCR selection, there could also be other kind of access controls. So for example, you could associate a password with a key, and the hash of the password can also be part of this access check access policy, so that the TPM will allow use of the key if the PCRs are in the expected value and if the user provided the right password. So the PCR information is part of the system state information. They come from the set of PCRs the TPM has, and the password of course comes from the outside. So this is the standard way TPM 1.2 works. So TPM 2.0 changes this by providing various kinds of logical combinations. So you can say, you can actually have a disjunction of different policies that are acceptable, and they can have this external authorization like we saw in this reference integrity metric. And they do that by introducing a construct called a policy session. So the situation is as before. You have a system, you have a TPM 2.0 inside it, you have an object that is that you want to protect, for example a key, and the object has certain reference values. And the objects are accessed by using some policy command, and the object authorization will check to see, based on these reference values, should the access be allowed or not. So in TPM 1.2 we only had PCRs as the way to, and password. Now we have TPM 2 requires that the way to access an object is to build up a session which they call policy session. And policy session, you can think of this as a kind of evidence collection mechanism. You start a session and then you say, I want to issue a series of policy commands which will culminate in this policy value, the check value being satisfied. And the policy commands are things like you can access, or you can extract things from the state information like PCR values, and you can extract information from other TPM objects like counters, things that are not PCR, like non-volatile counters and so on. And you can have external information like passwords, and you have external policy assertions like somebody else saying that if the current state is this, then you can go to a new controlled new state that allows things like this new versions of drivers and so on. So this policy session does all of this in a uniform way as opposed to TPM. So let me illustrate this by an example. So let's say that we have an object that's a key. So it's a private key, private decryption key. And the way you would, the operating system side would access this is by issuing a policy command. So let's say the policy command is RSA decrypt that identifies the key. So this is not the key itself, but a handle to the key. And then it gives some ciphertext. And at the time of invocation of the command, this object authorization check is going to decide whether this is allowed or not. And to decide this, it's going to depend on, or it's going to require the caller to build up a policy session. So the policy session is going to consist of a bunch of commands, and the last command is going to be this command. Right? So these commands are done in such a way that it will allow this authorization check to be done. So let's say that the policy that we want to enforce is that this should succeed if PCR1 has a certain value and PCR2 has a certain value. This is what we saw in TPM 1.2, right? And the way you would now embed this into this policy session is to use policy commands that would sort of bring this policy digest value into, bring the system state values into this policy digest. In a moment, we will see how these policy digest evolves. But I just want you to first see an example so that when I talk about individual commands, that would make more sense to you. So after you have built this, so every time you add a new command, this policy session has a value called policy digest, and the policy digest will change in a controlled way. And what the check at the end, after you have evolved the policy to a certain policy digest value, the check is going to be to see, does this policy digest value equal the guard value that is associated with the object, which is called the auth policy value. So this is the general kind of structure. So if you want to now bring in this PCR1 value, there is a TPM command that says called TPM policy PCR, and you say I want to take the value of PCR1 and I expect this value to be MOS. And if that is so, then this policy digest value will change in a controlled way. So it will start with 0 as the starting value. When you create a policy session, the policy digest will be 0, and every time you issue a command, there's a structured way in which it would change. And you can see already that the way it would change is you take the current value, you identify what command you are running, so it's policy PCR, and then you use parameters of this policy PCR like 1 and MOS, and you apply a cryptographic hash function, and this now the policy PCR value will go from 0 to this V11. And essentially what is done now is this V11 captures the fact that PCR1 must have value MOS, right? And then you do the same thing for PCR2, and you can also indicate what command you are going to actually try in the end. So you're building all this because you want to try a command which is access controlled. So you can say I want to try RSA decrypt command, and that's also kind of embedded here. So all of this will change this policy digest in a certain way. And now if somebody wants to enforce this policy, what they would do is to take this sequence of commands, find the last value that would be in this policy digest if you had followed this sequence of commands, and put that as the auth policy value. So essentially we have done exactly what TPM 1.2 does, but we have done in a certain structured way that will allow much richer and much more flexible policies, as we would see later. Okay, so in addition to checking that the current policy digest is the same as this guard value, the object authorization also does other checks. For example, it will check that some deferred checks still succeed. So it would check that the command that you are trying here is the command that you embedded here, like RSA decrypt, and the fact that this PCR1 and PCR2 still have the values that were embedded in the session before. So the object authorization consists of checking that the policy digest is the same as the guard value, and checking any other deferred checks. Okay? So this is just to give you an idea. Now I'll sort of go through the different kinds of policy commands that are possible in TPM 2.1. So policy commands are a way to change the policy session, and the policy session is the construct that so if you want to access something, you start a policy session and you issue a series of commands to collect evidence to prove that this particular command is allowed to be run. And the proof is gathered in this form of a policy digest. So policy digest is like a PCR, except that it's not it's part of a command session, and the policy digest is updated roughly the same way a PCR would be updated. You take the old value, so when you create a session, the policy digest is 0. When you issue a command, you take the old value, you combine that with the command that you're running, and then some command specific state information, and apply a cryptographic hash function, and that's how this policy digest would change if this command succeeds. So that's the general principle. And some commands, like this reference integrity metric that we saw earlier, can actually reset the value, so that it could say if a certain condition is satisfied, then the new digest value doesn't have to depend on the old digest value, but it can reset it to 0, but it has to remember the code and the command specific information. So this is how you can support multiple different ways of reaching the same policy digest value in the end. And we'll see how this is used later. And like I said, some of these can also have deferred checks. So these checks are done each time you, the policy digest is changed every time you issue a command. And then when you actually want to run a command, the system would check if policy digest is equal to the guard value, but it will also do a bunch of other deferred checks. Like if you imported a PCR value, it has to check that the PCR value didn't change while you are building the system, right? So this is to prevent against what is called the time of check to time of use attacks. Okay, so what kind of policy commands are there? We already saw that there is a policy command called TPM policy PCR, which is a way of saying that this particular access control depends on certain PCR having a certain PCR value, right? That's like TPM 1.2. But in addition to that, TPM have a bunch of other kinds of commands. So for example, you can say policy NV, which is like a way to refer to a non-volatile storage, like a counter, right? So you can say a counter should have a certain value, or it should have a certain relationship. So you can say counter 5 should be greater than 2 or less than 3, right? So if you issue this command, it will change the policy digest, but it will also remember or set up these deferred checks that you do later. We also saw this. So in addition to just saying that I want these PCRs to be a certain value, you can also say this is the command I'm going to try. And the policy session will remember that, which means that any other command will fail in that policy session. Only that command would succeed. So in the example we saw, we said that we are building this session to be able to try a decryption. And the only command that we can do is decryption. The more interesting things are this kind of policy disjunction. So there is a command called TPM policy OR, which works in the following way. So let's say that we want to associate a condition with some resource, like some key. And we don't know, so the end condition, which is like the ability to access a key, we want to support 3 different ways of reaching the same condition. So let's say that this is Windows, this is Linux, this is some other operating system. We want to be able to say you can boot Windows, you can boot Linux, you can boot, I don't know, some other operating system. And as long as you boot allowed versions of these, you will be able to decrypt this key. In TPM 1.2, we couldn't do that, right? There was exactly one way in which you could do. Now you could say something like the following. You could say if you had booted Windows, the policy digest would have a blue value. If you have booted Linux, it will have a yellow value, and if you have booted something else, it will have a green value. And now we could say at the point where you reach here, you can say, I want to issue a policy OR command that says the parameter can be any one of these. And if you do that, then the rule says that you can change if any of them, if the all policy digest is any of these, you replace this policy digest with a new value that contains a starting value which is 0, the command, and the list of all of these 3 hashes. So what this has achieved now is that you can boot whatever you want. As long as it's one of these 3, the policy digest is going to be the same value at the end, right? So now if you say, you don't have to say this key is associated with 3 different guard values. You can say the key is associated with just one guard value, and you can reach this guard value in one of these 3 ways. So that's called the policy OR. And the idea is that if you try to run this policy OR when the current policy digest is not one of these 3, then the policy OR will fail and the policy digest will stay the same. So for example, here you have a blue digest, blue which is the value of the policy digest, but blue is not one of the authorized values, then the policy digest stays as blue and you will not be able to issue the command at the end. Yes?
Can TPM tell who the requesting application is, not just the OS?
Not directly, but you can capture that in the PCRs, right? So you can say when you did the secure boot, you can say the PCR, the operating system is responsible for measuring the requesting application and putting that in a certain PCR, right? So you could have an example like that. And we'll see an example like this later on, which is maybe a little bit contrived, but secure boot depends on each layer to identify the next layer, right? So if you want to identify an application, you have to rely on the operating system. And the way you rely on the operating system is by first checking that the operating system is in the right configuration. And then you can say the operating system can identify the application and then extend the PCR with the application's measurements.
So I could store a key for a particular application.
You could.
Not use a password, like have the OS attest that this request for decryption came from a particular application.
Yes. So we'll see an example like this in a minute. Okay, so there is no policy conjunction. So like there's policy or, but there's no policy and. And I guess the reason is obvious, that PCR update is essentially a conjunction. You have to do in a certain way. It's not just a conjunction, it's actually also preserves the order. So if you want an arbitrary policy conjunction, then you can write a conjunction as a combination of disjunctions. So you can say, if you want to say D1 and D2 and D3, you write all the possible sequences and then do a policy OR at the end, right? The last thing that I want to say before giving you an example is this idea of external authorization. So let's say that, again, you have a guard value, you want to protect a key, but you want to guard, you want that key to be accessible to all versions of your applications, and you don't even know what the future versions of your applications would be. So if you just import the PCR of the application into this policy digest, it's going to have a value that you wouldn't be able to predict in advance. So TPM2 provides this way, a command called policy authorize to deal with this kind of scenario. So what this does is that if the current policy session value is a given value Z in this case, the operating system could provide a signature which matches this value, which is signed by some key. And so you can issue the TPM policy authorize command, and you can say here is a certificate or authorization signature. And TPM2 doesn't care what this signature is. All it would check is that is the value signed the same as the value that's in my current policy digest? If so, this command would succeed, but it will take the public key that was used to verify the signature and essentially extend reset the policy session value with the hash of that public key, right? So it's not exactly the hash of the public key, because it says that you reset it to 0 and you remember what command you used and you use the hash of the public key as a parameter, and that will be the new value. But conceptually we can say that you can go from some arbitrary value to the hash of the public key as long as this public key can be used to verify a measurement that matches this. So do you see this? This is how you can say if this public key belongs to a developer and the developer can authorize a new version of a driver at some later point, but he doesn't have to know that version of the driver at the time when he's setting up this access control, because the access control is going to be based on the policy digest having the value of a public key, his public key, and he knows his public key ahead of time. Okay? So that's the authorization mechanism. And this is what we saw earlier in this kind of external authorizations come from outside. Okay, so let's do this example once more, and maybe it becomes clearer. So the picture that I showed earlier, the scenario I had in mind was that there's a developer D, and the developer has somehow created a key pair on your device. So maybe they had an application that was running initially on your device, and it created a TPM protected key pair K1 using an application A. And he wants to make sure that only that application can access or can use key 1. So the key of course is never given out to any application because TPM protects that key, but it can allow the use of the key via this command like RSA decrypt. So the developer wants to make sure that this only this application A can access this make use of this key. And let's make a couple of simplifying assumptions. Let's say that this also should be possible only if you are running a certain operating system, and that operating system has a measurement that would be put into PCR1, and if you're running the correct operating system, PCR1 will have MOS. And let me also make the other simplifying assumption that in most mobile devices, at any time one application has the foreground, and we can arrange it so that the operating system will measure the application that is currently holding the foreground and extend that value into PCR2. So let's say that if application A is running in the foreground, then PCR2 will have value MA, right? So this is what we, so if this is the policy that we want to enforce for access to that key, then the question is what should be the auth policy of this key? And this is what we saw earlier, right? So you built a session like this, and you put as auth policy this value v13, that would be reached if you can do if you can import policy PCR1 having MOS and PCR2 having MA, and you are allowed to then use this command. Right? So this was a simple example which you could have done with TPM 1.2 as well. So now we can make it more complicated, and from now on I will not use this TPM2 prefixes because it just clutters up the space. I will just say policy PCR and policy command code. Okay, so let's say that the developer doesn't want to authorize only one application but wants to authorize 2 different applications, right? And you can see where this is going, right? So this if you have a application, another application PCR2 will have a different value, MA prime, and we cannot use this anymore, but we can use policy OR, right? So we can say that at this point we measure the application, we import the operating system, we import the application, and then we can say 2 different applications are allowed by saying that I'm going to issue a policy OR command, and if the current policy digest is v12 or v12 prime, they are both okay. So if I were running MA, this would succeed because you come to this point, and currently the policy the policy digest has value v12, and therefore this would succeed, and the policy digest will be now replaced by a value that depends on both of these. If I were running MA, and this is the value I would put as the guard value. If I were running MA prime, of course this would change. So v12, when I issue the second command to import this, policy session will have a different value at that point, but policy OR will again reset this back to this common value because policy OR says that these 2 are acceptable values. Okay? So this is this way I could have now said that 2 different applications are allowed to use this. Okay, so now the next logical conclusion is, what if we want to say y2, the developer wants to say any application that he develops should be able to access this. Right? So how would we do this? Again, we have to build up a sequence of commands which will end with this last command, and it should be done in such a way that at the end of this command, whatever the policy session value, that should match the auth policy. And the person who is setting up access control should be able to choose the auth policy value so that it will match for all allowed use cases. So we have MA prime, but we might also have some other new version of application or a new application, and we wouldn't know what the value of PCR2 would be. So that suggests that the auth policy cannot really depend on PCR2 value anymore because we don't know what PCR2 value would be. So we have to set up a sequence of commands so that this last value is independent of PCR2 value, but we still want to be able to say only applications authorized by this developer are allowed. Okay, so this is where we can use this external authorization command. So we build up the same way as before. We import PCR1, we import PCR2, we say what command we want to run, but then we will need to map this value to some fixed value that doesn't depend on PCR2. So like a naive way to do that would be to say, okay, let's assume that the developer has a key pair PKD SKD, and the developer will, every time he issues a new application, he will issue a certificate for that application that will have this form. So it will have a signature, and the signature will be the signed using his key, and it will have the value of the policy session if you have been doing the sequence of commands for that particular application. So if you were running MA, then the signature will have the value at the end of this third command, and if you run policy authorize is going to succeed because this signature matches this value, and therefore it will replace this policy digest from this value to a new value that is now independent of this PCR2 because it just says it's 0 plus the command and the public key of the developer. Okay. So if we were now running a new application which was not known before, so all of this would change. As soon as we import PCR2, this would change, and therefore v13 prime would change as well. But if the developer has issued a new signature, we will come back to v24, which is the same as before. So if that's the guard value, then this is going to succeed. Yes?
Every update the operating system causes us to break.
Right. So, but you can do the same thing with operating system. You can say somebody else, like the device manufacturer, is responsible for the operating system. So rather than importing the operating system alone here, we can put a policy authorize immediately after this. Right? So remember that I said we want to allow any application by this developer to be able to access this, this key. Do you see a problem with this construct that I have here? So the developer can, of course, authorize any application that he wants to use, but he can also actually authorize any operating system he wants to try and any command that we want to try, because we are doing this policy authorize only at this point, right? So he could say, instead of this being Windows, he could authorize some other operating system that would change this value, but when it comes to this point, it will be reset. So if you really didn't want the developer to authorize a different operating system or different command value, you have to make sure that the policy authorize is placed in the right order. So you import the application first, you let the developer authorize any applications by mapping from here to value that doesn't depend on PCR2, and you have these other values later on. Right? So this already should tell you about the pitfalls of this. This is a very powerful tool, but it also tells you that you have to be careful about how you structure this. And if you make a mistake, then your policy will not, you might not end up having the same policy that you want. Okay, so I'm not going to go through other examples, but you can imagine other cases as well. So you can say, well, the developer not only wants to authorize his applications, but he gets into some licensing business and he wants to authorize a different developer, D1's applications as well. And then you can go further and say he doesn't even know who he wants to authorize, but he wants to allow anybody whom he authorized to have access to this application. And you can put these kind of, you have a toolbox of policy authorize, policy OR, and policy PCR, and you can sort of play with these things. So these examples are in the slides. I'm not going to go through them, but I'll just try to sort of point out how this can be used with secure boot. So the one reason for doing all this is to be able to do secure boot. And if you remember, in secure boot we had this problem that how do we allow secure boot if there's a new operating system version or new driver version that should be still. Right, a key, you can say this is the object and here's the guard condition for this object. Boot is like a process, so we have to sort of have a proxy. So for example, we could say PCR5 is the proxy for secure boot, and we will say if at a given stage in the boot process, if you are allowed to extend PCR5, then boot will continue. If you are not allowed to extend PCR5 or PCR5, yes, then the boot is going to fail. So I'm just going to use PCR5 as a proxy for secure boot. And let's say that the operating system is measured into another PCR. So PCR2 has a certain value MA if a platform A kernel is loaded. So essentially I would do something like import policy PCR and say I'm going to do PCR extend, and if PCR extend would succeed, then the boot would continue. And now you can imagine that this will only allow this particular kernel to be booted. If I want to generalize that, I can bring in those tools that we saw before. You can say you can boot a choice of a kernel, or you can say we can boot any kernel that's authorized by this developer. So again, this has a more detailed example, but I think it's too laborious to go through that. So I'll just summarize the standard. So we saw these global platform mobile TEE standards. And like I said, I think it's a good foundation to be able to write trusted applications that are independent of the specific type of TEE. And we saw this TPM 2.0 library specification, which is also very rich. And this extended authorization model is powerful, and it sort of compensates for the brittleness of TPM 1.2. But one has to worry that is this too powerful and prone to mistakes in configuration, which will undermine the security. And we saw that even with all this, developers still don't have the possibility of using TE functionality arbitrarily for whatever application they want. This might change with the standards when they are widely deployed, but it still remains to be seen whether that happens or not. So in the last 7 minutes or 8 minutes or so, I want to sort of tell about some of the issues that are still open, and where there are researchers working on this, but no real solution. So the first one is this kind of we talked about these 3 mobile architectures, but there could be also new types of mobile TE architectures. And how is that? How can that be used? How does that fit into this architecture? This is one. The issue of open deployment, allowing developers to use this. This is the second one. How to get this trustworthy user interaction. And then what does this all mean to the user? And is this a good thing for the user, or can it also be used against the user? Okay, so I put up this picture of 3 different alternatives, but there are other possibilities, right? Somebody already asked about multiple cores. How can multiple cores be used? That's an open question. The other open question is, this one, we are still talking about smartphone class of devices or higher. What about the other end, where you have Internet of Things and sensors and so on? They can't afford the kind of security architecture that we have talked so far. So what kind of alternatives are needed there? So there's ongoing work in both of these areas. So for example, there's a paper that talks about how to use multiple cores with trusted execution environment. This is from CCS a couple of years ago. There's also recent papers from people in Intel labs in Darmstadt about low-end hardware security architecture for low-end devices. There have been also other researchers working on this. So I have links to all of this in the slides if you are interested. So both of these are still kind of, there's no definite winner or no clear winner, that there are alternatives proposed for these areas. The open deployment, we briefly touched on this. So on the one hand, centralized provisioning is sort of bad for the ecosystem, and I think the evidence of that is the smart card world, where even though technically you can run multiple applications on your SIM card, for example, in practice you don't, because if you're a small developer, you simply don't have the option or the wherewithal to go discuss with or make a contract with the entity that controls the trusted execution environment. And so that argues for having an open deployment model like we had in onboard credentials. But open model comes with other problems. One of the problems is liability and certification. So if you are using a smart card that's sent to you by G&D or some company like that, then they are responsible for whatever happens in the smart card. If there is like a failure in the payment system that's using the smart card, they are responsible for compensating Visa or MasterCard. If you are using a mobile device and the trusted execution environment and different developers can use this environment, it's not clear who will take the liability issue. If the mobile device developer has to, or manufacturer has to take the liability, they might not want to take the liability because they didn't even set out to do this as a general purpose functionality in the beginning. The second thing is that, again, we talked about this before, which is this kind of life cycle management. If you buy a new device, or if you lose your old device, so if you lose a device with all your credentials in that device, the first thing you want is that whoever steals the device shouldn't be able to use your credentials, right? And this is easily done. But the next thing you want is that you get a new device and you want all your credentials moved to the new device. And if you have been, if the device has credentials that are provisioned from all sorts of places, then it's not clear how they can be migrated in a user-friendly way. We had some ideas about how this can be done by using a centralized entity but not giving control to the centralized entity. The centralized entity doesn't decide what's on your device, it just helps you migrate. But that's a very, very preliminary step. The last thing is this, not the last thing, the one before last is this trustworthy user interaction that we talked about. So trustworthy user interaction is needed for various things like provisioning, user authentication, transaction confirmation. And there have been enough examples about how these, if you don't have a trusted user interface, how malware can interfere with all of these. And technical implementations are possible, but the question is, in the end, especially on mobile devices, it's a question of cost. The last thing is, what does this mean for user privacy? So, for example, in Germany, they are very much paranoid about TPM because they think that TPM can lead to user control because it can enable secure boot, and secure boot means that you don't have the freedom to run something other than what I don't know, Microsoft intends to. I think that's an issue of mechanism versus policy. So you can use secure boot and authenticated boot for good things or bad things. But on the other hand, the other aspect that, so there is all this functionality which can protect from malware to a certain extent and so on, but in the end it's software, and software can have vulnerabilities, and if software has vulnerabilities then it can be exploited, and then it can be, the game sort of goes from the operating system level to one level below. So there was already a trust zone based rootkit that was demonstrated a year ago. So none of this is a silver bullet that suddenly you sprinkle on it and you makes your device secure. It just gives you options, but one has to be aware that in the end hardware security still means software, because all of these trusted operating systems is written as firmware. Okay, so I think I will not repeat what I have already said, but I'll leave you with a bunch of pointers. So the slides of this talk, this talk and also the talk this afternoon are already on my homepage. So either you can go here or you can Google for me my name and you'll find this. There are a couple of papers that this is based on. So for example, we have an upcoming paper in a CCS workshop where we tried to use this TPM2 functionality to the kind of citizen electronic identification that I talked about. And the one sentence summary is that even with all this power, it turned out that we couldn't do the things that we wanted with the citizen identity in an elegant way. So we have some awkward constructions, and we suggest that you could extend this TPM2 in this and this following way, but that actually adds to this richness, which could be a potential pitfall. There are a couple of, there's a magazine article in the last issue of Security and Privacy magazine, which gives you a more accessible introduction to this information that I covered. And there's also proceedings of the IEEE invited paper on this whole area. And I think this is, well, in Technion, I think all of these are available freely, but this is open access, so you should be able to get it from anywhere. So that's what I had to say. Thank you for listening, and I think I can still take some questions.